Hello, thank you for watching this video. So in this video, we're doing question 10 of November 2023 question paper mathematics paper 2. And the topic is Euclidean geometry, as you can see over here. So let's go. They are saying in the diagram, PQRS is a cyclic quadrilateral such that PQ is equal to PR. Tangents to the cycle through P and R meet QS produced at A. RS is produced to meet AP at B. PS is produced to meet AR at C. PR and QS intersect at M. So, they're saying in this diagram, PQRS is a cyclic quadrilateral, right? No problem. Such that your PR and your PQ are equal, right? So your PR, this length over here is equal to this length over here, PQ. Fine. So your PQRS is a quadrilateral whereby your PQ and your PR are equal. That's what they're saying. They're saying tangent to the circle through P and R meet QS produced at A. So they're saying, as you can see, AR is a tangent and AP is a tangent, right? And AR is a tangent to the circle at R and AP is a tangent to the circle at P. So we're told that these two tangents, they intersect at A, where they intersect together with an extension of QS, because you can see QS is from here to there, and then QS is extended to A. That's where all these three lines intersect. That's what they're saying. They went on to say that RS is produced to meet tangent AP at B, right? That's saying RS, as you can see, RS is this length over here, is one side of this cyclic quadrilateral, is extended to meet the tangent AP at point B, right? And your PS that you can see here is what is the side of this quadrilateral PQRS, because you can see it's PS here. So this PS is extended to meet our tangent AR at point C. That's what they're saying. They concluded by saying that your PR intersects QS at M. So your PR intersects your QM at point M over there. No problem. We can see that. So 10.1, they are saying prove providing reasons that angle S3 is called angle S4. So they want us to prove that angle S3 is called angle S4. Where is S3? S3 is this angle over here. Let me use red ink. S3 is this angle over here, and S4 is this angle over here. So they want us to prove that these two angles are equal. Fine. So we're told a few things, right? We're told, the first thing that we're told is that PQRS is a cyclic quadrilateral. What is a cyclic quadrilateral? Fine. Let's go and start with that. So, you know, I'll start with a quadrilateral. Quadrilateral. What is a quadrilateral? A quadrilateral is just a four-sided shape. It's a four-sided flat shape, as you can see here. So this is A, B, C, D. Any four-sided shape, any four-sided flat shape is a quadrilateral. For example, you can think of your square, your rectangle, your rhombus. You can think of your those are parallelograms, by the way, all of them. All your parallelograms. You can think of your trapezium. The trapezium is a quadrilateral. Any four-sided shape, even this one, I don't even know what this is, but it is a quadrilateral because it's flat and you have four sides. So any four-sided shape is a quadrilateral. So now, what we want to talk about the cyclic quadrilateral. Quadrilateral. What is a cyclic quadrilateral? So, as you might think, of course, it should have something to do with a four-sided something. I don't know. It should have to do with if you're talking about a cyclic quadrilateral, it have something to do with a quadrilateral, right? So, a quadrilateral, you call it cyclic if all its vertices can be joined by a perfect circle. So if there exists a circle with a certain radius such that it connects all the corners of a quadrilateral, then that quadrilateral is cyclic. That's what a quadrilateral is. That's what a cyclic quadrilateral is. So, for example, let's say you have this quadrilateral over here, right? And you are able to draw a perfect circle that joins all the corners. Because you can see, this is a quadrilateral here. And all its corners can be joined by a circle, right? Or they lie on the circumference of the circle. We call that quadrilateral cyclic. So, now this quadrilateral, this one, is a cyclic quadrilateral. This is a cyclic quadrilateral because all of its vertices can be joined by a perfect circle. So think of this one as well. Yeah. So let's say you can say, let's say this is D, E, F, G. So this is this H, I, J, maybe K here. You can see even this one. This is a quadrilateral because it's four-sided. A quadrilateral is a flat four-sided shape, right? So now you can see all of its vertices are on the circumference, which is there is a circle with a certain radius that can join all of those, that can join all the vertices of that quadrilateral. So this is what these are things that we call quadrilaterals. These are quadrilaterals. So at least I would think that when they're saying P, Q, R, S, you understand what a cyclic quadrilateral is, which is it's a four-sided shape where its vertices lie on the circumference of a circle. Or maybe there exists a circle of a certain radius that can join all of its vertices. So if you're looking at P, Q, R, S, that is called a cyclic quadrilateral. You can say P is on the circumference, Q is on the circumference, R is on the circumference, and S is on the circumference. That's what it means to be cyclic. That's what it means to be cyclic. No problem. Now, what do we know about quadrilaterals? So, if this is the quadrilateral, let's say, because this is the quadrilateral, right? Let's say I were to extend, let's say this line was drawn such that it continues like that. So, H, I, J, K, let's say we have L over here. So what you need to remember about cyclic quadrilaterals, opposite interior angles of a cyclic quadrilateral are supplementary, which means they add up to 180. So this is, now these are cyclic quadrilateral properties. So these are the properties of your cyclic quadrilateral. So the opposite interior angles are supplementary, which means if you're looking inside your cyclic quadrilateral, the angles that are facing each other, they add up to 180 degrees, which is if you add this angle and this angle, it should be 180 degrees. If you add this angle and that angle, it should be 180 degrees. So if we're dealing with this quadrilateral, so in cyclic quadrilateral, in cyclic quad, H, I, J, K, H, I, J, K, right? We're looking at cyclic quadrilateral H, I, J, K. So we said that property number one, the opposite interior angles are supplementary. So one, we said the opposite interior angles of a cyclic, opposite interior angles of a cyclic quadrilateral are supplementary. Supplementary. What does it mean to be supplementary? Which means they add up to 180 degrees. In that case, what do we say? We say if we add I and K, if we say angle I plus angle K, this should give us 180 degrees, right? Which is these opposite interior angles are supplementary in a cyclic quadrilateral. Which is your angle H and your angle J should also be 180 degrees. Which is your angle H plus angle J should be equal to 180 degrees. That's one of the properties of a cyclic quadrilaterals, right? Which means in this case you can say R2 plus R3 plus P2 plus P3. That is 180 degrees because these are opposite angles of a cyclic quadrilaterals. In that case, you can say Q1 and Q2 plus S5 and S4. It should also be 180 degrees because those are opposite angles of a cyclic quad. Fine. That is property number one. Property number 2 that you should remember is that an exterior angle of your cyclic quadrilateral is equal to the interior opposite angle. Sorry, exterior angle of, equal to interior opposite angle. So if you have a cyclic quadrilateral, an exterior angle of a cyclic quadrilateral is equal to the interior opposite angle. What is an exterior angle of a cyclic quadrilateral? This is inside. So interior means inside, exterior means outside. So this is inside angle, inside angle, inside angle, inside angle. So all those 4 angles are interior angles, because remember that opposite interior angles, and all of those angles are interior. Now, what is an exterior angle? This is similar to an exterior angle of a triangle, right? So if you have one side of a cyclic quadrilateral, right, and that side is extended out, because you can see that KJ is extended to L. Your KJ here is reduced to L. So now the angle between your extended side and one of the sides of your cyclic quadrilateral is an exterior angle. So this angle here will be your exterior angle if you look at it. So an exterior angle will be the angle between the extended side of your cyclic quad and the other angle, and that angle should be less than 180 degrees, because it can't be this one here. You can't use, so it's the angle between the extension of one side and the other side, which will be whatever side will be the closest. In this case, this will be the closest side to the extension. It can't be this one, because this is itself. Fine. So in that case, we say this angle here, if say this is 1 and 2 here, we'll say our exterior angle J2 is exterior angle, right? J2 is an exterior angle. It's called the interior opposite, which is your exterior angle, your outside angle is equal to the inside opposite, because see, this is equal to this. So J1 is an interior opposite angle of H, and J2 is an exterior one because it's outside. So your J2 is equal to your angle H. One of the properties of your cyclic quadrilateral. So these are the properties that I will need you to keep in mind, right? So I will need you to remember this point. This is what a cyclic quadrilateral is. Fine. Now, let's suppose that we want to prove that a quadrilateral is cyclic. So, in this case, I was defining what a cyclic quadrilateral is. I said a cyclic quadrilateral is a four-sided shape where all of its vertices lie on the circumference of a circle. Or you call your quadrilateral cyclic if there is a circle with a radius that will be enough to connect all of the vertices of your quadrilateral. That's what your cyclic quadrilateral is. So now, let's suppose that I give you this cyclic quadrilateral. So I give you this quadrilateral ABCD. Let's say I give you that quadrilateral, and I want you to prove that that quadrilateral ABCD is cyclic. How do you prove that a quadrilateral is cyclic? That's what we want to do. Prove that quadrilateral is cyclic. So the quadrilateral that we look at is ABDC, because it's ABDC. The order matter. You can't say ABCD. Can't say that. So how do you prove that a quadrilateral is cyclic? Rule number 1. We must show that the opposite interior angles are supplementary, which is they add up to 180 degrees. That's the first thing that you need to show. You need to show that this angle plus this angle, they give you 180 degrees, and this angle and that angle, they give you 180 degrees. That's one way to prove that a quadrilateral is cyclic, which means, in that case, what we'll do, we must prove that angle A plus angle D, right, is equal to 180 degrees. Or angle C plus angle D is equal to 100. Or angle C plus angle B equal to 180 degrees. So in order to show that a quadrilateral is cyclic, you must show that this angle plus this angle, they add up to 180 degrees. That will be enough. You add there. You stop there. You don't have to prove this and prove that. One will do the work. If you prove that this and this is called 180 degrees, stop right there, because even these ones, they add up to 180 degrees as well. So you can stop right there. Or, now, what I'm saying, first way, prove that A plus D is 180 degrees, B plus C is 180 degrees. You don't have to prove both of them. Proving one will do the work. Stop right there. Number two, how do we prove this? How do we prove that ABCD is a cyclic quadrilateral? Let's suppose that our CD was extended, maybe to this point E here. ABDC, with CD extended to E. So what you need to prove that this angle here is equal to that angle over there. So if this is 1 and 2, which means you must prove that your exterior angle is equal to the interior opposite angle. That's one way. So another way, you must show that the exterior angle of your quadrilateral, of your quad, because that's not a cycle, it's a quad, is equal to the interior opposite angle. Which means you must show that your angle A is equal to D2. So which means you must show angle A is equal to D2. That's one way to go about it. So I've shown you two ways so far of showing that a quadrilateral is cyclic. One, show that the sum of two opposite angles are supplementary, which is show this and this called 180 degrees, or this and that's called 180 degrees. You don't have to show both of them. Show one to do the work. Two, what else do we do? The second way, I said that you must show that the exterior angle of your quadrilateral is called the interior opposite angle. That's the second way. The third way, how do you do it? Way number three. This one involves complex quadrilateral. You must show that a line segment of your quadrilateral, or 2 points, they subtend two equal angles on the same side. So you can learn more about this one on the bad actions, but I think these ones will be enough for us to work with this here. So you need to know what is cyclic quadrilateral, you need to know its properties, you need to know how to prove that a quadrilateral is cyclic. You need to know what an exterior angle of a cyclic quadrilateral. It is an angle between an extension of one side and the closest other side. And that angle, of course, is less than 180 degrees, right? Yeah. So I think I can clean the board and we can try to work with this now. At least I know that you are familiar with this, or I know that at least I've explained it. So you have no excuse to say you do not know. Let me get my my wipe and wipe the board. Okay, so now that we are done with recapping cyclic quadrilaterals, so let's do the questions. So the 10.1, they're saying prove giving reason that S3 is equal to S4. So they want us to prove giving reason that S3 is equal to S4. We said S3 is this one here and S4 is this one over here. Okay. Now, what you need to know, or what you need to remember, is that if you look at triangle, PQR, triangle PQR, where is triangle PQR? Triangle PQR. You can see that your PQ is equal, which is this side, is equal to PR. We're told this thing, we're given this information, it's on the statement. So you were told that your PQ is equal to PR. Fine. If your PQ is equal to PR and you look at triangle PQR, what kind of triangle is this? We can agree that PQR is an isosceles triangle. It's an isosceles. So what is an isosceles triangle? Isosceles triangle is a triangle with only two equal sides. So if you have a triangle A, B, C, and this side is equal to this one, then you have an isosceles triangle. Let's say this one side is equal to this one. You have an isosceles still. Or maybe we'll say this one is equal to that one. You have an isosceles triangle. So it's an isosceles. This is an isosceles triangle. Fine. What do you know? If you have an isosceles triangle, you know that two sides are equal, which is your BC in this case is equal to your AC. What else do you know? What you need to know about isosceles triangle, or what you need to remember, is that the angles that are facing the equal sides will also be equal, which is the angles that will be opposite equal sides will also be equal. So in this case, we have three angles: this angle here, and that angle there. So this angle C is facing that side, this angle B is facing that side, and this angle A is facing that side. So you can see B and A are facing identical sides, which is equal sides in length. So what does that mean? Which means this angle and that angle are going to be equal. So if you have an isosceles triangles, the angles that are facing, or the angles that are opposite equal sides, are going to be equal in length or in measure. So in this case, if you're saying your PR is equal to PQ, which is your PQ is equal to your PR, which means the angles that are facing those equal length are going to be equal. So in this triangle, we have three angles, this angle here. Let me use a red ink so that it is easy to see. So in this triangle PQR, we have three angles. This angle here, and that angle over there. So this one, angle Q, all of it is facing this side. This one is facing this side, and this one is facing that side. So as you can see over here, this angle is facing this side, PR, and this angle here is facing this side, which means this angle here is equal to this entire angle here. That's what you need to say, because these are angles that are facing equal sides, like I've said over there. So if you have an isosceles triangle, the angles that are opposite, identical, or equal sides, those angles will be equal in measure as well. So that's the case here as well. So that's what you need to know. So in this isosceles triangle of ours, this angle and this angle are equal. Right? No problem. So look now. If we start at S4, look at S4. Where is S4 coming from? S4 is formed by PQ. You can see S4 is formed by PQ. Right? Which is S4 is subtended by the line segment PQ, or this arc PQ. Now, the question becomes, is there any other angle that is subtended by the same PQ? You can see your PQ subtends here, your S4, and your PQ subtends there. What does it subtend? It subtends R3, right? But your R3 is equal to your Q1 and Q2. And look at your Q1 and Q2. Your Q1 and Q2 is equal to the exterior opposite. Your Q1 and Q2 is equal to the exterior angle of this cyclic quad, which means it's going to be equal to S3. But let me restart. So we said that in this triangle, PQ is equal to PR, which is PQ is equal to PR. Therefore, from this, we'll say, okay, now R3 is equal to Q1 plus Q2. Why? These are angles opposite equal sides. Right? These are angles opposite equal sides of a triangle. So we have discovered that these two are equal. So look now. I'm done with this. I'll come back to it. So let's start with S4. Actually, let me start with S3. It's fine. Look at S3. S3 over here. is an exterior angle of this of PQRS. If you look at this triangle PQRS, look, one side RS is extended to one side of RS is extended to B, right? So remember, I said an exterior angle of a cyclic quad is an angle between the extension of one side, is the angle formed by extension of one side and the closest side. So if you extend your PS to B, right? So the angle here is exterior angle. It can't be 180 because I said it should be less than 180 degrees. So in that case, S3 is equal to Q1 plus Q2. Why do I say that? S3 is equal to Q1 plus Q2. Why am I saying that? I'm saying that because S3 is an exterior angle of the cyclic quad, which is an outside angle of the cyclic quad, which is what I explained. So, going to say S3 is equal to Q1 plus Q2. This is an exterior angle of a cyclic quadrilateral. Because I said an exterior angle of a cyclic quadrilateral is equal to the interior opposite angle. Right? No problem. Look now. Your Q1 plus Q2 is equal to S3. The same Q1 and Q2 is equal to R3. Therefore, S3 is equal to R3. That's what you can conclude from this. Because if the Q1 and Q2 make R3 and the same Q1 and Q2 make S3, which is the R3 and S3 are equal, right? You can say, okay, therefore, R3 is equal to S3, because if S3 and R3 are both equal to the same thing, they should be the same as well. Fine. Now, we said our R3, right, is equal to this, right? No problem. And we said this is equal to that, which is these two are equal at this point. But look now, look at your R3. Your R3 is formed by PQ, right? Your R3 is subtended, your angle R3 is subtended by your PQ, and your S4 is subtended by the same PQ. You know that angles subtended by the same chord are equal. You know angles in the same segment are equal, which is angles subtended in the same segment are equal, right? So your PQ subtends this angle R3 and angle S4 on the other segment, because your PQ divides the circle into two parts, this small segment here and the bigger segment on the other side. So angle R3 and S4 are angles that are subtended on the other segment. And you know that angles in the same segment are equal because R3 and S4 should also be equal, because those are angles in the same segment, which is angles that are subtended by the same chord. So, in that case, we say R3 is equal to S4. Why? These are angles in the same segment, which is angles subtended by the same chord, if you want to say that. So look now, we said S3, okay, we said S3, which is this angle here, is equal to Q1 plus Q2. That is an exterior angle of a cyclic quad. And we said this is equal to that. Why? Because these are opposite angles, are angles opposite sides of a triangle. Now these angles opposite equal side. So, and this is equal to that. What does that mean? Because these are angles in the same segment, which is these two are also equal. Because if this is equal to this, and this is equal to this, and this is equal to that, then these two are also equal. Because you can see here, your S3 is equal to Q1 and Q2, your same Q1 and Q2 is equal to R3, your same R3 is equal to your same R3 is equal to S3, and your R3 is equal to S4. Or maybe I'm messing it up. Let's say S3 is equal to Q1 and Q2, right? And your S3 is equal to R3 and your R3 is equal to S4. So which means your R3, actually, your S3 and your S4 are equal, which is what you want to prove. You can say, therefore, S3 is equal to S4. So it's clear. Because you can see here, your R3 is equal to S4 from what we've explained here. Because if this is equal to this, and same thing is equal to that. These two are equal, which is what I've written there. And you can get that your R3 is equal to S4 now, right? But look now, R3 is equal to S3, and your R3 is equal to S4, which is these two are also equal. That's what I did. This is what they want us to prove, and we're done with this question. Now we're going to move to 10.2. What are they saying? They are saying prove that SMRC is a cyclic quad. So they want us to prove that SMRC is a cyclic quad. What is a cyclic quad? I said a cyclic quad is a quadrilateral that can be joined perfectly by a circle, which means there is a circle, there is a perfect circle that can connect all the corners or all the vertices of your quadrilateral. That's what it means for a quadrilateral to be cyclic. Fine. So they want us to prove that SMRC is a cyclic quadrilateral. How do we do that? So where is SMRC? Let's go and identify it first. S, where is S? There is S here. M here. R, there's R. C, there's C over there. So they want us to prove that these 4 points, they want us to prove that SMRC is a cyclic quadrilateral, which is that quadrilateral SMRC. They want us to prove that it is cyclic. I've said 3 ways of proving that something is cyclic. But to define it, which means there exists a circle. If you're saying it is cyclic, you are saying there is a circle that connects all 4 of them perfectly. That's what it means. This is what you mean, which means you're saying there is a circle, which is there exists a circle. Let's say we draw a circle. This is what you're saying. You're saying there exists a perfect circle that will connect all 4 of these points. That's what it means to be cyclic. So, how do we prove that a quadrilateral is cyclic? I said we must show that the exterior angle of a cyclic quad is equal to the interior opposite angle. That's the first one. The second one, the opposite interior angles of a cyclic quadrilateral are supplementary. And the third one, you must show that one side of your quadrilateral subtends equal angles on the same side, or 2 points subtends equal angles on the same side. So if you look at this, you have that, you know, if SMRC is your cyclic quadrilateral. This is your quadrilateral. It's not cyclic yet. We're still trying to prove it. So your SMRC is a quadrilateral, right? You want to prove that it is cyclic. One thing you need to do, one of the way to prove that the exterior angle is called the interior opposite angle. So where are the exterior angles of this thing of yours? So one should be this one over here. This is an exterior angle. So if this is our exterior angle, the interior opposite angle is that one. We don't know anything about that angle. Is there more? Yes, this is an exterior angle. Because look, if you extend CS of the cyclic quadrilateral to P, this will be exterior angle. Right? Your CS, because here is your quadrilateral. Right? SMRC, SMRC, SMRC. If you extend one side, CS to P, this is your exterior angle here, S4. But S4, we already proved that it is equal to, S4 is equal to R3, and your R3 is equal to Q1 plus Q2. Which means your S4 is equal to Q1 plus Q2. So, here's what we can say. If we're saying this is our exterior angle, the interior opposite angle, where is it? Because if this is our cyclic quad, so if this is our quadrilateral here, and this is our exterior angle, the interior angle is that one over there. So this is our interior opposite angle over here. But look, the interior angle is made of R1 and R2. The angle between your tangent, right, and this chord over here. So this is your tangent over here. This is your tangent. And this is your chord here. This is the chord here. And you know the time chord theorem. You know the time chord theorem. It states that the angle between the tangent and the chord is equal to the angle that the chord subtends on the other side. So if I have a circle here, right, and I have a chord here, or maybe let me draw this as is, right? So let's say we have a tangent at this point over here. So if you have a tangent, the angle between the tangent, right, which is the line and the chord, is equal to the angle that this chord subtends on the other side. So this angle and this angle are going to be the same. The angle between the tangent and this chord, this is our tangent and this is the chord, would be equal to the angle that this chord subtends on the other side. So this angle will be equal to that angle over there. That is your time chord theorem. So in this case, the angle between the tangent, this one, which is the tangent, this one, and the chord, will be equal to the angle that this chord subtends on the other side. So essentially, what I'm saying is that this angle here is the same as this angle, and you know this angle is equal to that angle over there. So the angle between the tangent and the chord is equal to the angle that this chord subtends on the other side. But this angle is equal to this one, and this one is equal to that one, which means now you will have proved that this exterior angle is the same as the interior opposite angle. So what do you say? You say, okay, R1 plus R2, this angle, R1 plus R2, is equal to Q1 plus Q2. Why am I saying this? The angle between the tangent and the chord is equal to the angle that this chord subtends on the other segment. So in that case, we'll say this is our tan, what is our tangent? AR, chord. What is our chord? RP. So in this case, we've shown that the angle between the tangent and the chord is equal to the angle that this chord subtends on the other segment. Then, you know, Q1 and Q2, this angle over here is equal to this angle here. You did mention this. Why? We said these are angles opposite equal sides, which is Q1 plus Q2 is equal to R3. Right? So, let me just write it, just for clarity's sake. So I'll say now, the same Q1 plus Q2 is equal to R3. These are angles opposite equal sides of a triangle. Right? No problem. And this is equal to this one, which is your R3 is equal to S4, which is what you prove here. R3 is equal to S4. These are angles in the same segment. So you say R3 is equal to S4. Why? These are angles in the same segment, which is these are angles subtended by the same chord. Right? So look now. We're saying your R1 plus R2 is equal to Q1 plus Q2. Your Q1 plus Q2 is equal to R3. Your R3 is equal to R4, which is these two things are equal. So what we'll say therefore R1 plus R2 is equal to S4, which means you prove that the interior angle is equal to, which means you prove that your S4, which is the exterior angle, is equal to the interior opposite angle. So this thing is cyclic. So say therefore SMRC is a cyclic quadrilateral, right? Why? Because the exterior angle is equal to the interior opposite angle. That's what we did. We've shown that this angle here is equal to that angle over there. We're done with this question. Move to the next one. So, what are they saying? We're doing 10.3. I'll clean the board, right? Or let me clean the entire board, and then we'll do 10.3. So let's clean the board. Okay, I'm done cleaning the board. Now we're going to do 10.3. 10.3 reads as follows. Thus improve given reasons that RP is a tangent to the circle passing through P, S, and A at P. So they're saying RP, you can see RP here. That's saying RP is a tangent to a circle that passes through P, S, and A. Let's say you have a circle P passing here, here, and there. Let's say there is a circle that passes through these points, right? Maybe it's not very nicely drawn. Let me just try to do this. Okay. Okay. Yeah, looks better now. So, they are saying, let's suppose that you have a circle that passes through P, S, and A here, right? That's what they want us to do. Actually, they are saying that let's suppose that we have a circle that passes through P, S, and A. They are saying if there's a circle that passes through P, S, and A, the line PR is a tangent to that circle at point P. So they want us to prove that RP or PR is a tangent to the circle that passes through P, S, and A. So what is a tangent to a circle? So if you have a circle here, a tangent is a line that touches your line at exactly one point, right? Tangent is a circle that touches is a line that touches your circle at exactly one point. How do you prove that a line is a tangent? So now we're proving that a line is a tangent. How do we do this? If you are trying to prove that a circle, a line is a tangent to a circle, one, you must show that your line is perpendicular to your radius, which means if you join this is the center, of course. If you join the line to the center, this angle should be 90 degrees. You must show that they are perpendicular, right? That's one way. What is the other way? You must show that if maybe, let's say, we have some sort of circle like this, right? And let's say you have this triangle over here, maybe. If you can show that the angle between your line, your line, if you want to show that this line is a tangent, you must show that the angle between the line and the chord is equal to the angle that this chord subtends with the other segment, which will show that the angle between the line of yours and the chord that it intersects at the point of contact, which is at the circumference, is equal to the angle that this chord subtends on the other side, which is also, or you can also show that the angle between your line, which is this side, and this chord would be equal to the angle that the same chord subtends on the other side. So that's the other way. So way number two, you show the converse of the tan chord, which is you must show that the angle between the tangent, to show that a line is a chord, you must show that the angle between the line and to show that a line is a tangent, you must show that the angle between the line of interest and the chord is equal to the angle that the chord subtends on the other side. That is the opposite of the tan chord. That's the converse of the tan chord theorem. So if you want to show that PR is a tangent to a circle passing through P, S, and A, it's either you show point number one or point number two. But to show point number one, you must have the center and you must have some sort of radius or maybe your diameters. But in this case, you are not told that B is a diameter, is a center. So you can say that AP is a diameter. So you don't know anything about the radius so that you can comment maybe on its orientation in relation to the line. So this one is out already. But you can try something like this. Because in order to do this, you need to know a lot about your radiuses or your diameters or your centers. But you don't know anything about the center of this circle because you're told nothing about it. right? So what we want to show now, I think we should show that the angle between the line, this line here, and this chord, because you can see that PS is a chord to this circle over here, PSA. So this is the chord. If you can show that this angle is equal to this angle over there, we have done this because, look, this is similar to what we're talking about there, because the angle between the line and the chord is equal to the angle that this chord subtends on the other side. Angle between the line and chord, which is this angle, equal to the angle that the chord subtends on the other side. So now if you can show that the angle between the line RP and the chord PS, that is P2, is equal to the angle that the same chord subtends on the other side. You can show that your P2, if you can show that your P2 is equal to A2, you will have proved the second way. So let's try that. So how do we do this? It would be difficult to talk maybe about P2 alone, right? But look, if you look at the entire angle P1 and P2, this is a tangent in its own right? This is a tangent. AP is a tangent. So the angle between the tangent and this chord is equal to the angle that this chord subtends on the other side. So this angle P1 and P2 is equal to that angle there, which is angle Q, right? So this angle is called angle Q. You know angle Q is equal to this, and this is equal to this. That's what we've proven so far. So we know that we can say now this angle here and this entire angle are all equal. But look, this angle here, if you're looking at ASP as a triangle, if you look at ASP as a triangle, S4 is an exterior angle of that triangle. So which means S4 is equal to the sum of the interior opposite angles. So what I'm saying your P1 and P1 and P2 are equal to what? Are equal to Q1 and Q2. Right? So this angle here is equal to that angle over there. Why? This is the tan chord. What is your tangent? Your tangent is AP. And your chord is RP. I've explained the tan chord. So the angle between the tangent and the chord is equal to the angle that the same chord subtends to the other side. But you know this is equal to that. So your Q1 plus Q2 is equal to R3. Why? This angle and that angle are equal. We said those are angles opposite equal sides. Right? No problem. Now, your R3 is equal to S4 because these are angles that are subtended by the same chord PQ. So these are angles in the same segment. So you say now R3 is equal to S4. Why? These are angles in the same segment. Right? So you say this is equal to this is equal to this is equal to that. Therefore, these two are equal. Therefore, P1 plus P2 is equal to S4. So we have shown that P1, if you add this P1 and P2, they give you S4. But S4 is an exterior angle of triangle ASP. If you look at ASP, if you extend AS maybe to Q, you can see that this is an exterior angle of this triangle. So in that case, you can say the S4 is equal to the sum of the interior opposite angle, which is A2 plus P1. We say this is an exterior angle of the triangle. In that case, the S4 is equal to S4. Therefore, P1 and P2 is equal to A1 and A2. So P1 and P2 is equal to A2 and P1. So this and that go away. You get that P2 is equal to A2, which means this angle over here is equal to that angle over there, which is the angle between the line and the chord. It's equal to the angle that the chord subtends to the other segment. So this thing is a tangent. So that case, say therefore, what is it? RP is a tangent. Why? Say the angle between line and chord is equal to the angle in alternate segment. Yeah, which is the angle between the line and the chord, which is the angle between your line RP and the chord is equal to the angle that this chord subtends on the other side. These two angles are equal. Then you have proved that this thing is a tangent. And I believe we're done with question 10. And I hope it does make sense to you as it does to me. So let's go to the next question. Thank you for watching. Cheers.